Hi everyone. So this video is basically a discussion of a very interesting analogy between what momentum in optimization for training machine learning models does and the phenomena in physics, which is basically physical drag. And physical drag happens when there is a solid body that moves in a fluid, in a gas or a liquid. So for example, when you're swimming, the water pushes back against you. When an airplane moves in the air, the gas is moving against the force which the plane pushes for, right? So basically the idea is very similar. So think as if you have a particle, and the gradient is a force that's imposed on that particle, right? And the alpha v, or the contribution of the past gradients, which is the term that's added by the momentum algorithm, is basically the resistance of that medium, right? So it's the resistance of the water, for example, right? So I'm putting force, a new force. I'm trying to move, I'm trying to swim in water, but then there is an accumulation from so in that analogy, the accumulation of the past gradients, compare it to the basically the force or the resistance that the water puts back on you, right? And then eventually, right, if these forces are against each other, so that fraction, eventually you lose energy and you stop, right? So you get tired when you swim, right? And much more than if you walk, for example. And so think of it this way: if I am around in a point here, and this is my cost function, again one-dimensional parameter space, and so the gradient tells me at this point to move in this direction. So let's say epsilon is not very small that I move here. No, I would move to the other side, right? Now without momentum, I could keep oscillating forever between these 2 points, right? What momentum does is that if the new gradient is in an opposite direction, so it will take a smaller step, right? So then maybe I move the next time here, right? And then the next time I have an even smaller step, so I move here, and then the next time here, and then I stop, right? So it accelerates the process of stopping whenever the gradient direction is inconsistent, right? So that can also help a lot, especially if the cost function itself has highly inconsistent gradient directions, right? Like exponential in some regions. So instead of that causing a lot of problems in navigating the parameter space, this inconsistent gradient direction can make us stop, right? And so that's a useful analogy, is to think of navigating the parameter space as if you're applying, in every iteration, you're applying a force on a particle, and that particle is a solid mass, and the parameter space or whatever you're navigating is a fluid. And that fluid applies a drag that's proportional to the past gradients, right? So think of the past gradients as basically changing the nature of the medium that you are navigating, okay? And basically, if you think of other, like if we think of that analogy as inspiring us to come up with momentum algorithms, so think of other alternatives. If so this is basically the alpha v term corresponds to a particular type of drag, which is called viscous drag, right? Where the v is to the power 1, right? So that's the effect of viscosity in physics, right? If you have what's called dry friction, that's a constant friction. So if you have remember that the v term is typically has a magnitude that's far smaller than 1. So v to the 0 is a very large value compared to the gradient, right? So that can make us basically stop, right? Can make us stop too early before exploring enough of the parameter space. Now, the other extreme is what's called turbulent drag, and that's corresponding to V square. V square can be very small. If the drag is very weak, then that can cause the particle to move away its energy is not consumed early enough, or maybe never, right? So it can keep moving away from its initial position forever. So from empirical evidence, that kind of viscous drag, or the correspondence to V to the 1, or the alpha V term, seems like a good balance that eventually result in the parameter updates losing energy, right, and stabilizing and reaching equilibrium. Thank you.